Hello, before we go ahead and write the ADC header file and source file, let us run our program. Okay, it looks like the program is compiling, but there is a mistake here. We are reading something, right? And we want to return at least a character. That is a bad mistake. So make sure you correct this and go to the UART header file and also change the return of this, the read. Okay, make it a character. Perfect. At this point, go ahead and open the ADC.h. Just like with the other peripherals, with the GPIO peripherals and also with the UART peripheral, we are going to get some registers. I always say in a normal program, you will put all the registers of a particular peripheral into a struct, but we are not doing that. We want to get the individual registers that we need. And one thing, make sure that the UART, you include the header file. I realize it. Make sure you include it. And also in the GPIO source file, make sure you include the header file. Else when you run it, you might get a mistake. Now ADC header file, the first thing that we will do is to include the base header file. Once we are done with it, we can take a look at the data sheet. But already we've taken a look at it and we know that the ADC peripheral is connected to the APB bus. Alright, it's connected to the APB bus. Let's look for the ADC okay, let's see. ADC registers. Okay, ADC, the register should be here. Okay, yes, right here, ADC registers. The first one is the interrupt status register. Let's go there. So copy it and I'll search for. Alright, okay, ADC interrupt and status register, and it's a 32 bits. Most of the bits are reserved. More importantly, we need this bit 2, and we can take a look at bit 2. Is the end of conversion. So for ADC, before you can read the value and it has to be converted, this bit is set by hardware at the end of each conversion of a channel when a new data result is available in the ADC DR register. So when you want to read ADC value, you have to first of all check this register and see if the conversion is completed before you can read. So we will create enable bit for this bit 2, but before we do that, let us get this register. It is at an offset of 0x00 ADC ISR. So come back here and let us define ADC ISR. First we define offset, okay, and the offset is at 00. Then we define the register ISR. We will call the ADC peripheral that we defined in the base header file. So if you go to the base header file, we define the ADC peripheral, ADC header file. So ADC peripheral plus offset. Now we have the register. Let's define the bit ISR EOC, end of conversion. And the end of conversion was at bit 2. We will read this bit. Let's call this enable bits. When we are done, we will cut it into the source file. End of conversion EOC. That is the first register. The next register that we are interested in is the control register. The control register is always important because we will need to start the ADC module and also we need to enable it, and we do all of that in the control register. Okay, this is the ADC control register. It is at an offset of 0x08, and when we take a look at the register, it's 32 bits from 0 to 31. Most of the bits are reserved, but right here we are interested in the ADEN, enabling ADC, and also ADC start. Let's take a look at it. Bit 0 ADEN, that is ADC enable command. This bit is set by software to enable the ADC. So for this to work effectively, we need to write high to that bit. The ADC is effectively ready to operate once the ADRDY flag is set. So now let's get this, and also the ADC start conversion command. It's also set by software to start the ADC conversion. So we can see it flows. First of all, you need to enable ADC, right? You have to start it, to allow conversion, and before you read the ADC value, you have to check end of conversion using the interrupt state register. So most of the time, the interrupt state register, either is ADC or UART or any GPIO, is there for you to check it when something is done. So you get these 2 bits, but for now the register is at this offset. We can copy it, go to the IDE and CR offset 0x08. Then we define the register ADC peripheral offset. Perfect. Now I said the 2 bits that we will need at least for the start is bit 0 and bit 2. Later on, for example, if we need to calibrate the ADC, we could even use this, but for now we will use the default calibration. So let's create a macro for ADEN and AD start. We define ADEN bit 0. We also define CR AD start, and that is at bit 2 registers. We will also need the configuration register, and we will need the channel selector and the data register itself. Let's take a look at the configuration register. Go back to your reference manual and okay, so we have the configuration register here, and what we need from the configuration register is bit 13, and sometimes you can choose to align the values, and also we can choose to set the scanning direction. For example, if we are using multiple ADC, so about 3 pins, they are all ADC values which are being connected by different sensor modules, and we want to scan them in a particular direction. Okay, let's say we have a thermometer, we have heart rate monitor, and we have a variable resistor value, and we want to read the values in a particular order. We could use the scan direction, but for now let's take a look at bit 13. Okay, this is continuous or single conversion mode. If you set it to continuous conversion, it means the ADC keeps on converting. If you set it to single, then it converts to a particular point and it stops. So as we can see, this bit is set and declared by software. If it is set, conversion takes place continuously until it is cleared. Alright, let's get this register. ADC CF, let's copy it. Offset 0x0C. So we define the offset A. Okay, let's paste what we have. 0x0C, and we define the register, then ADC peripheral plus offset. Now that we have the register, let us look at the bits that we will need. We said we would take bit 13. Bit 13 is this. Let's create a macro for it. Define cont bit 13. The next bit that we need is the channel selector. A quick look at my dev board, you can see it has analog and digital pins. So right here we have A0, A1, A2, A3 and A4. Now those pins, you can set the pin mode to analog. We are going to do that in a minute. We will do it in the source file. So once again, we will need the register to select which pin we want to use, whether we are using A0 or A1 or A2, and that register is the channel selector register. So we have ADC channel selection register. It is at an offset of 0x28. We copied this register. It is at an offset of 0x28, offset 28. Now from this register, we will need channel 0, which means that we will connect our ADC sensor to A0. That will be GPIO A0. We can just define channel select get bit 0. The next register that we need is the data register. So once the ADC has completed the conversion, the value can be found in the data register. So let's quickly go to the reference manual and look for the data register. Yeah, this is the data register. It is at an offset of 0x40. We get the offset. Go back to your IDE offset and we define the register itself, DR ADC peripheral plus offset. Now we need our last register. We need the RCC register that is responsible for enabling clock access to the ADC peripheral. Okay, let's look at that. Let's look at the block diagram. Okay, so this is the block diagram. ADC is connected to the APB. Then let's go ahead and search for the RCC registers. RCC, it brings me to the RCC, but I need the APB. Okay, APB enable register 1. So let's see if we can find our ADC peripheral here. I don't see it. I don't see ADC. So if there is 1, then there is 2. APB peripheral clock enable register 2 and bit 20. Yes, so bit 20 is for enabling ADC clock. We'll get this register. This RCC register. Let's copy it, come here, offset 0x40. Then we define the register itself. RCC peripheral plus offset. So more or less, these are all the registers that we will need for this particular project. You could use other registers. Once we have all the registers, let us forward declare our functions. With the ADC, we will need to initialize the ADC peripheral. We will need to do conversion. It reads the ADC value, it needs to convert it first. We will need to sample the ADC, and we want to transmit the ADC. So we read the ADC from whatever sensor is connected to it, then we will transmit it via UART to the computer we are using. So let's write the functions. First, we will need void ADC init, ADC conversion, right? The next will be ADC read. The next function will be sample ADC signal. So in this function, we would like to pass a buffer to it, and also we will give it a pointer to our program state. The next function is to transmit signals. Just pass the pointer to the buffer. This is pretty much the end of the ADC header file. But as usual, I like to cut the enable from the header file. I like to take it from here and move it to the ADC source file. I paste it. And in the ADC source file, we should include the ADC header file. Then I go back to the ADC header file. Let's copy the function prototypes here, ADC, and paste them. Now we can give them bodies. This is where we are going to define them. Let us start with the initialization. Now we have our ADC header file set and ADC source file. So when we created the RCC APB ENR2 register, the register that is responsible for enabling clock access to the ADC module, we said we needed bit 20 as is indicated over here. So let us create the macro to store this. Let's define RCC ADC enable, and that is bit 20. A few steps are required to initialize ADC module. First, we need to allow clock to ADC module. After allowing clock access to the ADC module, what we can do is, and because we will connect the ADC module to A0 as I showed you guys. I mean, you can choose A1, whatever it is. Because of that, we need to set GPIO A0 mode to analog. Okay, at this point we will go to the GPIO source file and do that configuration. After setting that, we can go ahead and set data resolution. Now once we go into the configuration register, we will see that the ADC can convert values in different resolutions. With this particular board, it can give you values in 12-bit, 10-bit, or 8-bit. The lower the data resolution you are picking, the faster the sampling rate. So after setting the data resolution, you select the channel in the channel select register. After selecting the channel, we can go ahead and enable the ADC module, which most of the time we do in the configuration register. Now to allow clock access to the ADC module, we will use the RCC register responsible for the ADC module, and we have declared it over here, right? This register. Go ahead and copy it back to ADC source file. We can paste it, and as we always do, we enable that bit, and that should be RCC ADC enable. Now the next point, that is configuring pin 0 port A to be analog pin. All right, let's go to the GPIO source file here, and let's give a comment. Set GPIO A as analog mode, right? Go and get your reference manual, and here we will go for the GPIO registers. With the mode register, depending on the pin you are using, you have to choose one of these. Because we are setting pin 0 port A as analog pin, we are dealing with mode 0, and mode 0 occupies bits 0 and 1. And to set it as analog, we need to set both bits to 1 GPIO A mode R register. And since we have already defined the GPIO A mode register, and if you want to know, we define that in the GPIO header file. Go to the GPIO source file and let's set mode 0 to analog. We are setting both bit 0 and bit 1 to 1. So we can write GPIO A bit 0 to 1 and also mode R bit 1 to 1. Alright, the pin mode is set. We go back to the ADC source file. This is set in the GPIOC. Now we need to configure the data resolution, and with the data resolution we are going to use the configuration register that we have set. Let us go back to the ADC header file. We already have the register. We are going to use this. Before we do that, why don't we look at the ADC registers and see ADC registers. Let's check the configuration. Scroll to the configuration. Okay, this is the configuration register, and as we can see, bit 3 and 4 represent the data resolution. Let us scroll to bit 4 and 3 and see how we can configure data resolution. These bits are written by software to select the resolution of the conversion. Let us set both bit 3 and 4 to 10 bits. Go back to ADC source file and let's call the ADC configuration to set bit 3 to 1, and then bit 4 we set to 0. Alright, the next thing that we need to do is to select the channel that we want to use, and definitely with this we are going to use the channel selector register right here, ADC channel selector. Let's go ahead and copy this and let's paste it. But how do we set the channel? We looked at the channel selector register, and actually you can see here we already selected channel 0. But still, if you do not understand, what we did is that we went to the ADC, we were in the ADC and we looked at the channel selector. Okay, this is the channel selector, and you can see the channels ranges from 0 to 18. This lines up with the number of pins in each port, right? We are choosing channel 0. We have defined it right here, channel 0. We copy it and let's just leave it like this. Now to enable ADC module, we are going to use the ADC control register, which we have already defined here, ADC CR. And the ADC CR, we have gotten the enable bit here, ADC CR EN. This is all that we need to do to configure ADC peripheral. Now, how do we perform ADC conversion? The ADC module is reading a value and it needs to convert it before we can use it. To do conversion, we are going to use the configuration register, set continuous conversion, and start ADC module. This is the configuration register, and we are interested in setting the continuous conversion to ensure that the microcontroller keeps on converting the values. So that was bit 13 right here, and we set it to 1 because we want it to do it continuously. We copied this, we go back to the ADC source file, and we already defined the conversion mode, which is here. Okay, we've already set it. We will paste the register. We've set it to continuous conversion. Once we are done, then we will call the ADC control register and set the ADC start. This is the ADC control register. You can see bit 0 is for enabling the ADC module, right? And bit 2 is for starting. Bit 0 to enable command write and to start. Go back to the ADC source file, and with the conversion we need to start ADC CR, and this time we will do the ADC start, which we have defined here, AD start. The ADC conversion function is done very easy. So let's go to the ADC read function, and with the ADC read function, always we look at the interrupt status register and see if, let's say, a value is available Once a value is available, we return the ADC data register. Now, when we look at the ADC header file, we already defined the interrupt status register. And in the interrupt status register, we need to read a particular bit that will tell us if a value is available in the data register. And that value was the ISR EOC, that is end of conversion. We need to check whether the conversion is ready or not. I think we can use a while loop here. ADC ISR, we use and compare with the ISR end of conversion. As long as this evaluates to true, then we are stuck in the while loop, because if there is a value in the data register, then this will evaluate to 0 and the while loop will not run. It will go to the next line. Once there is value in the data register, then we can go ahead and return the data register. We are going to write the ADC sample function in a way that when the blue LED is on, then we go ahead and sample signals. Sampling signals means that we read ADC into the buffer that we have provided. When we are done with sampling, we will call the transmit signal and we pass a pointer to the buffer to it. Let's define few variables. Let's check the state of the program. If the program state is equal to on, let's create a pointer to the starting address of the buffer that we have passed. So I'll use the UART byte to read the ADC, and I'll use this byte 1 to get the first byte of the UART byte. Once our program state is on, we can do a simple for loop. Then we will use this UART byte and we will set it to ADC read. So once it returns this value, we will take the first UART byte. Let's do AND with 0xFF. So I'll take the first byte and put it into the buffer, byte 1. Alright, once the sampling is complete, we will call the ADC transmit signal and we pass the pointer. With the transmission, definitely we have sampled 64 signals, so we will transmit 64 signals. We will do a simple for loop here. We will call UART write, okay, and we will pass in buffer. We will do this. Since we are calling UART here, we need to include the UART header file, usart.h. Alright, this is what we have in the main function. We will just go ahead and read the analog signals.